Hi everyone, this is Kellen Bilodeau here to talk about the Physics 2211 Lab 2 motion of a falling object. For my intro, the goal is to observe, measure, and make conclusions about the motion of an object that is dropped from rest and falls somewhat slowly straight down. The models that we'll use for measuring this is one physical, which is going to be filmed and then placed in the tracker software, and then two computational models, which are going to be coded models to make predictions about the motion of the object. One is going to use gravitational force, and one is going to use both gravitational and drag forces. The hypothetical result is that the computational model only modeling gravity will fall more quickly than the physical, while the computational model with both gravity and drag forces included will model the physical model more closely, though with some errors. The main physics ideas is the first one is Newton's second law, in which case we're going to be talking about the net force, right, which we can define as the change in momentum over the change in time, which in this case specifically we're talking about the drag and gravitational forces, where the net force is going to be negative because the gravitational force is greater than the drag force. That is until we reach terminal velocity, but we'll talk about that later. The next force we're going to talk about is gravitational, right? So it's m times g times j hat, and the j hat is the vector that shows us the direction. We're using 0, 1, 0 because it's vertical. You can derive this using the generic gravitational force equation, and note that any falling distance that would add to the Earth's radius is insignificant because of the Earth's massive radius in comparison to any distance that I could drop the object from. The next force is the drag force, which is negative a constant b times the speed squared times v hat. And v hat is also vertical, but it's moving downwards. So we're going to specify that it's 0, negative 1, 0 as a vector. An assumption that we're making is we're using the variable b, which is the combination of like several more specific variables that are hard to define in this case. So we're just calling it b because we're only looking for the relationship between the two computational models. So the systems and surroundings, we're using the scarf as the object. The material that is falling through is air, which is going to provide the drag force. The earth is going to provide the gravitational force, and the ground is going to be the thing that stops the scarf. Our initial conditions, right? The initial velocity is going to be 0 because I'm holding it. And the initial position, I am defining up in the air as 0, and I'm going to be moving in the negative direction. The physical model, you can see that I drop it, and it accelerates as it falls because the gravitational force is greater than the drag force, and you can see that reflected in the model on the left. The first computational model is the one with only gravity. The equations that we're using is the gravitational force, and then we're using velocity update, and then position update. We define our initial conditions in the code. We define our equations down in the bottom of the code so that it can calculate those values and display them in the graph on the right. I will show you the velocity graph later as we get into the physics discussion. The next computational model is the gravity and drag computational model. And this time we're going using drag force. Drag is actually positive because it's opposing the negative force of gravity in this case. And to calculate b, I just adjusted b until the final output of the graph is the same as the physical model, just so that we can make that comparison. So the comparison of these three graphs, right? We have the position of the tracker, we have the position of the two computational models. If you look at the very last point on this graph here, the y value of the computational model using both gravity and drag is the same as the one of the physical model, but at about like halfway through, so t final over 2, y of the tracker is actually lower than either of them. So that shows that something else is going on here. So this is a possible source of error. My assumption is that there is an uneven drag force on the system. And an example of this is like a wing. So the way that wings gain lift is by unevenly distributing drag forces. Velocity graph on the right, it's not always going like at the same speed. It's not always constantly decreasing. The drag force is being unevenly distributed across the area of the scarf. So some of the questions that we're going to be asking are, which models, if any, predict the terminal velocity? Right. So if we look at both of these models, which is the gravity model and the gravity and drag model, the gravity only model is just a line, and the second model is a curve. Obviously, the first one, the velocity is always going to be changing. Acceleration is always going to have that negative value. But for the second model, acceleration is going to reach 0 at some point as that curve approaches the asymptote. And that at that asymptotal value, that's when it reaches the terminal velocity, right? So it's when acceleration is 0, right? F equals ma. F net is going to be 0, telling us that the F and D value, or the gravitational and drag forces, have become equivalent. They're balancing out, and it's moving at a constant velocity in the air. The second one is, if you were to throw it down with an initial velocity, uh, would there be a different terminal velocity? And the answer is no. If you look at the changes that I made to the code, which is to change the initial condition of velocity, both terminal velocities are actually the same, just below that -8 value. So terminal velocity is a value derived from the object and the material it's passing through. Initial velocity has nothing to do with it. It might reach it a little bit quicker if you have a higher initial velocity, but it's still going to approach that same value.